All right, so we're just going to be reviewing what we did in class today in terms of looking at forces in 2D, right? Two dimensions. So now our forces are not going to be necessarily the nice, neat, one force is vertical and one force is horizontal. They're going to delve into sort of, a portion of the force is horizontal and a portion of the force is vertical. Similar to our study of motion in two dimensions, trigonometry is going to be really important to this. So knowing a little bit of geometry, knowing SOHCAHTOA, and knowing when to use those things are going to be really important to figuring this out. So I just want to do probably the first two steps of solving these problems with you right now. And like I said, we went over them in class today, but I just want you to see them again because it can be a little confusing, and this way you can slow it down and go at your own pace. So here in this scenario, we have a box that is stationary, right? So it's just kind of sitting on this pretty steep incline, right? It's a 60-degree incline. So if we were asked to identify the forces and their magnitudes on this box, right? We want to know what are the forces and what are their magnitudes. The first step, right, is going to be to identify, is it balanced or unbalanced, right? So the forces on this box are going to be balanced. So it follows the balanced force model. And we know this because it's not accelerating in any direction. Right? It's stationary. So the second thing here, right, is to identify the forces and maybe do, in this case, a rough sketch of the free body diagram, right? What's acting on. So if this is the box, right, we know that there's some gravity acting on the box, and gravity is always going to be straight down. Right, there's our force of gravity. And then with this angle, things get a little trickier, right? Normally, we would have the normal force, right? If this box were on a flat surface, right, the normal force would be pointing up, directly canceling the force of gravity. But the normal force, by definition, acts perpendicular to a surface, right? So the normal force is actually going to be acting perpendicular to the force of, the angle of this surface, right? Fn is going to be perpendicular here. So it's not directly canceling gravity. It's some magnitude at an angle, right? We'll draw a little dotted line here. The dotted line is not a force. It's just to sort of represent the surface, right? And then we're going to have some friction force here, right? That's fighting the box sliding. So it's going to be upward, right? And some friction, and it's going to be static friction, right? Because the box isn't moving. If it were sliding, it would be kinetic friction. So that's what our free body diagram looks like here. And this can be a little confusing to set up, right? But if you remember that normal force has to be perpendicular to any surface, right? That should guide you, right? Gravity is always going to be straight down to the center of the earth, right? And normal force is always perpendicular to the surface that is in contact with the object, right? So, if this box were sitting on a flat surface, we'd have it pretty easy, right? If it were sitting flat and not moving, right, we would have, well, that's not straight, but whatever. Fn would be kind of straight up, and Fg would be straight down, and since it's not moving side to side and it's not floating up and down, we would know that these two forces equal each other, right? We can't say that here, right? We can't say that Fn equals Fg, because this Fn is pointed not directly canceling the Fg, right? So we've got to do a little bit of legwork to figure out the equivalent values here. And the first really important thing is to determine the angles that are happening in here, right? And I like to think of the easiest way to do this, right, is to sort of do a little geometry here, right? If we were to draw a line that was pretty parallel here to this line, right, and use the interior angle hypothesis, right, or theorem, whatever you call it in geometry, right, this angle is going to be 60, right, and this one's going to be 120, right, that's something that we know, right, and we know here that this gravity here is 90 degrees, right? So from that, we can kind of determine what these different angles are, right? We have enough information to determine what these angles are. So let's see. I like to think about shifting, sort of rotating this so that now this is our x direction and this is our y direction. So if you like think about just tilting your head slightly, right? That's now your plane that you're used to working in. And we're going to want to figure out what components of x and y there are of fg, right? Now, let's see if I can draw this, right? Our coordinate plane is now shifted so that it lines up with Fn and Fs, right? They're within our two dimensions that we're working with. And Fg is the only one that falls outside of those dimensions, right? So Fg is going to ultimately need to be split into some components, right? It's going to need to be, right, if this is Fg, we're going to need to find, right, there's going to be a Fg in the y direction, Fgy, and an Fg in the x direction. Right, and if we split those up, we can see, right, that, you know, if this is, right, here is Fgy, and this is going to be Fgx, right, Fgy has to equal Fn, and Fgx has to equal the static friction, if the box isn't moving, right? So this is tricky, but it's sort of a matter of kind of shifting your view on it, right? So the question is, how do we determine the angles of these triangles? Because we can find Fg, right? If we have the mass of this box, say it's 20 kilograms, right? We know that Fg is going to equal mg, right? So we could find the hypotenuse of this right triangle. I'm going to draw this a little bigger down over here so that we can see it a little better, right? We can find the hypotenuse of this triangle, right, Fg, because we have the mass and we have little g. So if we can figure out what these angles are, right, or even just one of those angles, we can determine, right, using trigonometry what Fgy is and what Fgx is, right? So this angle here, right, if we're to go back to sort of our picture here, right, Fg is sort of straight down from the box. This is Fg, right? And it actually forms a triangle here with this 60 degrees, right? Which is really interesting. So you can actually apply the shape of this regular triangle here, right? I want to see if I can make this a little clearer here, right? Do you see this? This line here is Fg, right? Straight down from our box, right? and it would generally come straight down from the center, but this shows it a little better, right? And this forms with the inclined plane a right angle triangle. Do you see that? Right here. Right, so given what you know about triangles, right, you can figure out this angle, right? It has to be 30 degrees because this triangle has 60, 90, right? It has to equal 180, right? So we now have the angles for our triangle in here, right? We have 30 and 60, and we can go ahead and solve for FGX, right? This one right here. I'm just going to use the 60 angle, right? FGX is going to equal cosine of 60 times FG. Right? This should look similar to the work that we did with projectile motion, right? Remember, the cosine of this angle equals adjacent over hypotenuse, right? So cosine 60, just to show you where I got this from, equals FGX over FG, right? Multiply both sides by FG, and you get the above equation. Right, so we can solve for FGX. Whoop. Right, and once we have XGF, we actually know the static friction force because they have to equal each other because the box isn't moving. Okay, so understanding this bit of it, right, that actually these two pieces, the rotation of your coordinate plane and also the sort of mirroring of the triangle on top of the free body diagram are really, really important for having this stick. And we're going to be doing a lot more practice with this in the coming weeks. All right, see you guys later.